Welcome to the lesson 19 of industrial instrumentation. In this lesson we will basically cover the low pressure measurement. In lesson 18 we have seen that we have basically discussed the medium and high pressure measurements, but low pressure measurements also is a part of interest for, even though not much for the industry, but for the academics and also scientific community. So, the low pressure measurement also is very much necessary, and it is a different class of instruments. We will find the principle of operations of these instruments is also totally different. So, let us look at lesson 19, low pressure measurement. The contents of these lessons are Mcleod gauge. We will see, we will cover the Mcleod gauge, then we will cover the Pirani gauge, then thermocouple gauge, ionization gauge and Knudsen gauge. Now, you will see that the Mcleod gauge actually, I mean these are all these pressure gauges you will find it they have different application as well as different range of the pressure measurements. It all lies between 1 torr to 10 to the power minus 10, 10 to the minus 12 torr. Torr means 1 millimeter of Hg. So, that will come. What are the different units of the pressure measurements, that we will discuss after some time. Now, in some instruments you will find it is basically monitoring sort of instruments or indicating instrument, but some instruments you will find we will get electrical output. So, we can utilize it all for control, for transmission, all those facilities will be available. We will particularly see that the Mcleod gauge and the Knudsen gauge. So, let us discuss for the Mcleod gauge. So, at the end of this lesson, so we will know all the details of these type of gauges. Also, we will consider some problem solving. We will make some problems and we will give the solution to some pressure gauges, diaphragm gauges especially, and also on the Mcleod gauges, right. Now, before going to the details of the pressure measurement, let us look at the units of the low pressure measurements. The different units are 1 micrometer equal to 10 to the minus 6 meters of mercury, or sometimes we call it micro mm or micron, which is 10 to the minus 3 millimeter of mercury. And now 1 micron means, or you see that if I say that 10 to the minus 3 millimeter of mercury, that means 10 to the minus 6, if it is SI unit, 10 to the minus 6 into the density of the liquid multiplied by the acceleration due to gravity, that will give you the pressure. So, 1 micrometer is equal to 10 to the minus 3 millimeter of mercury, equal to 0.133322 Newton per square meter, right. And 1 torr you will find it is 1 millimeter of mercury. 1 torr is the lowest pressure measuring units. So, we call it 1 millimeter of mercury, right. So, 1 millimeter of Hg or 1 millimeter of mercury. Now, let us look at the Mcleod gauge. The Mcleod gauge is considered to be a vacuum standard. We will find that the pressure can be computed from the dimensions of the gauge. It is very important, it is independent of the so many parameters. So, it can be used as a pressure standard. The principle of the Mcleod gauge is the compression of a sample of the low pressure gas to a pressure sufficiently high to read with a simple manometer, right. We will compress a gas, low pressure gas, to such a value, so that we can simple manometric principle I can measure that pressure. That is the basic principles of the Mcleod gauge. A low pressure gas will be taken and it is systematically or very intelligently will compress it to sufficiently high pressure, so that a simple manometer method I can measure the pressure. That pressures will be calibrated in terms of that low pressure actually in which we are interested, right. So, that is I am saying the principle of Mcleod gauge is the compression of a sample of the low pressure gas to a pressure sufficiently high to read with a simple manometer. Reading is most important, reading is independent of gas composition. That means I can take any gas, so I do not need I do not have to recalibrate the instrument. That is a great advantage of the Mcleod gauge. This advantage is not there, you will find in other low pressure gauge like ionization gauge and all those things, it is totally different. Let us look at more details of the Mcleod gauge. You see, this is the schematic of the Mcleod gauge. You see what will happen, you look at very carefully. You see here we have a movable reservoir, right. So, this reservoir I can move it up and down, this can be moved up and down. This is a flexible tubing, even though we have drawn like this one, this is a flexible tubing, these are all flexible rubber tubing, right. It is connected to this movable reservoir. The reservoir can go up and down. Actually, there is a frame, like things through which this reservoir actually moves, right. Now, we have a capillary here, you see this capillary we have. Now, principle is that first this movable reservoir will go down. If I keep it go down, you see the mercury from this reservoir is coming and it is filling up all this. You see it is coming through this region, it is coming and it is filling up to this level. So, according to this will be the same, this should be at the same level. Now, what will happen when once I move this reservoir downward is all this mercury in this tube as well as in this capillary and the bulb will be collected in the reservoir, fine. Now, if I put the mercury below this level, below this 0 level, you see what will happen. The gas in which we are interested to measure the pressure will enter. Okay. So far it cannot come down. Now, once I push the mercury down here at this region, then what will happen? You see this mercury will come, this gas will come down and it will enter this region, this capillary. Slowly it will enter the capillary also. So, basic principle is we will push this movable reservoir down as long as mercury comes down to this 0 level. Now, I push this reservoir, move this up, then what will happen? If I if they push this reservoir up, then what will happen? You see the gas which is trapped inside this capillary and also the bulb, okay, will start to compress. Once it start to compress, it will give some, because it is getting compressed and compressed, it will give some pressure for which the mercury column cannot rise to this level. Now, this height, this blank height will be calibrated in terms of the low pressure. This is the basic principle of the Mcleod gauge, right. Again I am telling this movable reservoir will come down, all the mercury will be collected here, because this is a flexible tubing, I should say this is a flexible tubing. Right. So, it will come down, all the mercury will be collected in the reservoir, the gas will be trapped here, it will come down this position, then it will come down, gas will come through this region, it will enter here, then it will go up. Now, I will slowly move this reservoir up, then what will happen? Simply the trapped gas will be getting compressed and compressed, mercury column is going up, as I move the reservoir up, this mercury column also will go up. And this compressed gas is getting compressed and compressed and it is giving a back pressure to this mercury column. So, after a certain time we will see that even though we have taken the reservoir at this level, this mercury cannot go up because of the pressure created by the compressed gas, right. So, that the region where that mercury cannot reach will be calibrated in terms of low pressure. This is the basic principle of the Mcleod gauge. Right. So, this will be elaborately we will speak in the next slides. The movable reservoir is lowered until the mercury column drops below the opening 0 or O, whatever you say. The bulb B and the capillary C are then at the same pressure as the vacuum source P. Now, one thing is important, you see this bulb B is purposefully made quite large compared to the capillary. We will see the mathematical relation why it is made large, right. So, this is made quite large compared to the volume of the capillary. This is the volume of the total capillary. So, height multiplied by the area of cross sections of the capillary, that should be much less compared to the volume of the bulb, right. The movable reservoir is lowered until the mercury column drops below the opening O. The bulb B and the capillary C are then at the same pressure as the vacuum source P. This is actually the pressure which I want to measure. This is the pressure. This P is the pressure which I want to measure. The reservoir is subsequently raised until the mercury fills the bulb and rises in the capillary to a point where the level in the reference capillary is located at the 0 point. What is that reference capillary? Let us look at again. This is our reference capillary. So, until unless this reservoir is this mercury column in this reference capillary coming to this 0 level, I will move the reservoir up and up, right. Once it comes to this 0 level, I will stop moving the reservoir in the upward direction, right. The reservoir is subsequently raised until the mercury fills the bulb and the rises in the capillary to a point where the level in the reference capillary is located at the 0 point, right. Area of the capillary is denoted by area of cross section of the capillary, I should say, denoted by A. So, the volume of the gas in the capillary is Vc into B subscript C, that means capillary, equal to A into Y, where you see this, where Y is the length of the capillary occupied by the gas, right. This is the length of the capillary which is occupied by the gas. What is that? I should go back again. You see, this is the length of the capillary occupied by the gas. Sorry. Okay. So, I should say this is the length of the capillary occupied by the gas, right. This is our Y, and this is the area of cross section is A. This is the area of cross section. So, obviously, this volume V C capillary volume, this volume will be equal to A into Y, clear. Where Y is the length of the capillary occupied by the gas, right, that is true. Let the volume of the capillary, bulb and the tube down to the opening be Vb. So, you see that Vb is not only the volume of the capillary, it is volume of the capillary, bulb up to the point 0. I should refer back again. You see the volume of the capillary, that means I am telling the volume of the capillary up to this level. So, this total volume I am telling is Vv subscript V, clear. So, let the volume of the capillary, bulb and the tube down to the opening be Vb. If we assume the isothermal compression of the gas in the capillary, we can write that Pc, that means the gas which is compressed, equal to P, actually that which we want to measure, equal to Vv capillary, I mean this valve volume divided by the Vc, the capillary volume, is equation number 1, right. This actually gas was in pressure P. Okay. Please note, it was in the pressure P. Now, I have compressed to Pc, right. So, which is higher compared to P, clear. So, it should be in such a high conditions or such a high value that I can measure by the simple manometer. That is the basic principle of our Mcleod gauge. Now, the pressure is indicated by the pressure indicated by the capillary is Pc minus P, okay, that compressed pressure minus the pressure actually which I am interested to measure, equal to Y, right. If suppose if it is in, I mean if I divide it by D and G, so obviously I will get that also in Y, that is in height. This is equation number 2, because in obviously it should be divided by D and G, the density and the acceleration due to gravity, to get the expressions of the pressure only in height, where we are expressing the pressure in terms of the height of the mercury column, right. Now, combining 1 and 2, we get P equal to the unknown pressure equal to Ay square upon Vb minus Ay equal to Y Vc divided by Pv minus Ay. For most applications, I can say the volume of the capillary is much smaller than the much smaller than the volume of the total volume of the capillary, then valve up to the leveling opening O of the mercury. Actually, in fact, you know that's actually the what will happen. For most applications, I can take that Ay is much less than Vb. So, I can write now it is clear that why I have taken Vb much greater than Ay purposefully, we are using a bulb, that is the reason, there is no need, otherwise without bulb also system will work. We have taken so that I can write the unknown pressure P equal to A y square upon V b. You see A, the area of cross section, the capital D is constant, V b is the area of the bulb, then capillary as up to the opening of the this Mcleod gauge, this is also constant. So, A is the P is directly proportional to P square, even though it is not linear instrument. So, E is y square, right. With this approximation we will introduce obviously some error, because we have approximated by this, right. Commercial Mcleod gauges have their capillary calibrated directly in the micrometers, right. The Mcleod gauge is sensitive to the condensed vapor that may be present in the sample, because they can condense upon the compression and invalidate equation 1. So, we should be careful about that. For dry gases, the gauge is applicable to the 10 to the minus 2 to 10 to the plus 2 micron, which is equal to 0.0013 to 13.33 Pascal. Now, Pirani gauge, it is now this all about the Mcleod gauge. Now, Pirani gauge is basically based on the thermal conductivity. Basic principle is something like that. A gas, a heated filament will be placed inside a chamber, but there is a heat transfer from that chamber, from that heated surface to the outer surface, colder surface. Colder surface is the glass envelope, which is actually in which actually the those heated filament will be placed. And as the number of molecules decreases, there will be less heat transfer from the heated filament to the cold world or the colder surface. So, the temperature of the heated filament, the filament will rise. So, that temperature, so obviously if the temperature rises, so the resistance of the heated filament also will rise. So, that if I put that in the Wheatstone bridge, so I will get unbalanced voltage, that unbalanced voltage is calibrated in terms of the low pressure. That is basic principle of the Pirani gauge. It looks like this, you see at low pressure the effective thermal conductivity of the gases decreases with pressure. How? That is I said that if the pressure decreases in a vessel, then what will happen? Why I am getting the pressure? Kinetic theory of gases says that I am getting a pressure in the vessel because there is random motions of the molecules. So, it is hitting the surface of the walls which is actually creating the pressure. If the number of molecules decreases, also the pressure will decrease, right, because there is less number of molecules in the, if the less, or in other way, if the pressure is low, number of molecules in the vessel also will be low, right. So, what will happen that I have, it looks like this, okay, we will show in the next slide that what is the basic principle. At low pressure, the effective thermal conductivity of the gas decreases with pressure. The Pirani gauge is a device that measures the pressure through the change in thermal conductance of the gas. An electrically heated filament is placed inside the vacuum space. So, it will be clear, you see here. Heat loss from the filament is dependent upon the thermal conductivity of the gas and the filament temperature. Lower the pressure, lower the thermal conductivity, because you see that as the pressure decreases, the number of molecules also will decrease, is not it? As the pressure decreases, number of molecules also will decrease, right, and higher the filament temperature. So, temperature of the filament will rise, okay. Temperature of the filament if rises, its resistance will rise. So, the bridge unbalanced current also will, unbalanced voltage will also increase. So, that unbalanced voltage will be actually will measure, right. The resistance of the filament is measured by a bridge circuit, right. Now, you see this is schematic of a Pirani gauge, it is not actual Pirani gauge. You see what will happen here. I have a fitted filament, so I have a number of molecules here, is not it? It will be very clear from this diagram. Molecules are here. So, what will happen? You see this connected to the vacuum space, where in which I am interested to measure the pressure. So, the filament, this molecule will hit this, okay, this will come in contact with this heated filament, and it will take away due to random motion, it will go, and this surface is cold surface compared to the heated filament. So, this heat will be taken away in this direction, is not it? So, as the number of molecules decreases, as the pressure decreases, the number of molecules also decrease. So, there is a less chance of taking the heat away from the heated surface to the colder surface. So, what will happen at the pressure decreases, the temperature of this heated filament will rise. If the temperature of the heated filament rises, then what will happen? Its resistance also will increase. Now, if I put in a bridge, if I measure this change of resistance by some in one way or by some means or the other, I will get some change of resistance. So, that change of resistance either I can calibrate in terms of voltage or current, that will be calibrated in terms of low pressure. That is the basic principle of the Pirani gauge, right. Now, what actually happened, you know, they have a coiled tungsten wire, they have a coiled tungsten wire like this one, okay. Several wires are there, 4 wires, usually they will find there are 4 wires, okay. These wires are placed in a vessel. The wires cannot, I mean, suspend like this, there must be some arrangements by which it is to be hold inside this chamber, right. Let us go back again. So, this is a schematic of the Pirani gauge. Now, see, this is a bridge circuit is actually used for measurement of low pressure by Pirani gauge. Now, you see, because since it is a resistance devices, so it should be changed, it should be affected by the ambient temperature variations. If the ambient temperature changes, so what will happen? This resistance will change. To avoid that, you will use 2 Pirani gauges, okay, and put on a 2 arms of the Wheatstone bridge, right. And one particular gauge which is compensating gauge, okay, as it happens in the case of Wheatstone bridge we have seen, in the case of strain measurements we have seen, this is called a dummy gauge. Okay, this will be compensating element. So, this will be evacuated at very low pressure, then it is sealed, right, and this will be as usual the normal Pirani gauges, which is when the low pressure will go inside through this region. Now, what will happen? You see, if due to environment temperature change, if there is any change of temperature due to any change of resistance, so there will be similar change of resistance here in the same, because these 2 gauges elements are also exactly identical. So, the ambient temperature variations or bridge unbalance due to the ambient temperature variations will be totally nullified if I use this type of configurations, right. So, this is called the compensating element, okay, or dummy gauge, dummy Pirani gauge. You see this is evacuated and sealed. Now, there is a balance spot. I will explain what is the function of this balance spot. Initially we need it, because once you put this gauge and this is also at a low pressure. So, we will see, we will balance these bridges, that means, you will make the resistance in the 2 arms exactly equal, then I will make it null. Okay. Now, the unknown pressure will go inside. Initially these 2 gauges are the same pressure, please note, these 2 gauges, that means these gauges, these dummy gauges, this dummy gauge and this gauge were at the same pressure, right. Now, and I will balance using the balance spot, I make these 2 resistance equal, because these 2 resistance may not be exactly equal, there are only slight difference. So, I will use this balance spot to make these 2 resistance in the 2 arms, that means arm from this region to this and this region to this exactly equal. If it is equal, then what will happen? So, it will be totally balanced, right. Now, the unknown pressure will be go inside. So, I will get a bridge unbalance, that bridge unbalance will be calibrated in terms of the low pressure. That is basic principle of the Pirani gauge, right. Now, the resistance element is in the form of a 4 coiled tungsten or platinum wires, as I have shown, right. The cold surface is a glass tube, the outer surface of the glass is a cold surface, okay. 2 identical tubes generally are connected in the bridge circuit to avoid the change in bridge output due to change in ambient temperature. One of the tubes is evacuated to a very low pressure and then sealed off, while the other has the gas admitted to it. The balance spot is then adjusted to produce null condition, right. We have used that null condition, I have explained that thing. To balance the bridge initially, the pressure in the measuring element is made very small and the balance spot set for 0 output. Generally, the bridge is used as a deflection rather than a null devices, okay. any change in pressure will cause a bridge unbalance. So, this unbalance will calibrate in terms of, you see this is the bridge unbalance current in microampere of Pirani gauge by a pressure. Now, see after some time as the pressure increases there is saturations of the bridge unbalance current, there is a definite reason why it is coming saturation. This is the current in microampere 100, 200 microampere, right. So, as a low pressure it is quite good response I am quite change I am getting, but at high pressure when the pressure is coming beyond 1 torr, so it is getting a saturation, there is no change, and in fact if the pressure increase further there is no change in the bridge unbalance current, right. The calibration, you see the gauge must be calibrated against some standard, it is not suitable for pressure below 1 micron. The upper limit is 1 torr, 133 Pascal, giving an overall range from 0.1 to 100 Pascal. For a higher pressures, the thermal conductance changes very little with the pressure. Okay, thermal conductance changes very little with the pressure. It must be noted that the heat loss from the filament is also a function of the conduction losses to the filament supports and radiation losses to the surroundings, right. The lower limit of the low pressure measurement by Pirani gauge is the point where these effects overshadow the conduction into the gas, right. Now, Pirani gauge, one of the greatest drawback, it has a large time constant, it is not the, the measurement is immediate. So, that is one of the greatest drawback of the Pirani gauge, right. The establishment of the thermal equilibrium may need several minutes because it takes a thermal system, so it may take several minutes before it settles down. Now, this thermocouple gauges will find its response time is quite fast, even though it is slightly different principle, but its response time since in the if you compare with the Pirani gauge is much less in the case of thermocouple gauge. The basic principle is like this, you see, this is also based on the thermal conductivity. What is that? I am saying that there is a gas molecules are there, okay. So, these gas molecules will try to take away, this is a heated filament. So, we are with some battery, we are heating this filament, this is a heated filament, okay, this is our heated filament, heated plate rather I should say, okay. So, principle is same, instead of coil I am using the heated plate, so this will be heated. So, as the temperature as the pressure falls, there is a less chance of the molecules to take away heat to the colder surface here. This is a cold surface glass tube. So, the temperature of this with the same current, the temperature same battery voltage, what will happen, the temperature of this heated plate will increase. There is one thermocouple welded here, okay. So, that will measure the fall or rise of temperature, okay, of this heated filament, because if the temperature rises, what will happen, if the pressure increases, then what will happen, that temperature actually the filament will fall, filament current will fall if the pressure increases, is not it. Why, you see because there is more chance of the heat to be taken away, so that is reasons the pressure will fall, the current will fall or voltage will fall, right. So, what will happen, you see in that type of situation, so I will measure the temperature, right, I will measure the temperature, and this temperature is, or in this millivolt is calibrated in terms of the low pressure. That is the basic principle of the Pirani thermocouple. This also basically depends on thermal conductivity. That means, as the pressure increases, the current will decrease or voltage will decrease, because it will have a less temperature rise if the pressure increases, right. So, it looks like this, the response curve will be look like this one, okay. So, like this one, as the pressure increases in torr, okay, the current or voltage, okay, of this thermocouple voltage will fall, right. So, as the pressure decreases, what will happen? So, less number of molecules try to heat this one, so its temperature will rise. So, this filament temperature, this heated plate temperature will rise. So, you see here, so as the pressure decreases, okay, here you see that temperature will, the output voltage will rise. So, that is measured by the thermocouple, you see. Hot surface is a thin metal strip I am still discussing about the thermocouple gauge. Its temperature may be varied by varying the heating current. For a given heating current and gas, the temperature assumed by the hot surface depends on pressure, obviously. This temperature is measured by the thermocouple welded to the hot surface, right. Gauge is not independent of ambient temperatures change because there is no such bridge arrangement or something like that. So, that the advantage what we have using a dummy gauges or compensating gauges in Pirani gauge, in Pirani measuring systems, that is not there, absent in particular the thermocouple gauge, right. So, range is typically 10 to the minus 4 to 10 to 1 torr. Range is also I should say is not that good. That good means it cannot measure that low pressure, right. Now, third pressure gauge I should discuss is ionization gauge. Ionization gauge is the one of the gauge which can go to extreme low pressures. Okay, this is the lowest pressure measuring devices. It is the basic principle is that it will try to ionize some gases, and that ion current that ion will be collected by some plate, and that current will be measured. Now, let us look at this ionization gauge. You see, this is a chamber in which we put the gas in which we are interested to measure the pressure. We have a cathode, we have a grid, and we have a plate. Now, you see there is always some electron will lie here, right. So, this electron will be collected by this plate, is not it. So, electron will emit here, it will collected by the plate. There is no doubt about that, fine, because there is number of electrons will be large here. Now, if I put some gas inside, what will happen? If I put some gas inside, while this electron by this high voltage, you see this 400 volt, will try to will accelerate from this to this position, it will knock out some of the electrons of the outermost shell of the gas molecule. So, that gas will be ionized. If that gas is ionized, then what will happen? You see, this, since this is a, you see this is the connected to negative terminal of the battery. So, ion will be connected by this grid or ion collector, we gave it the name grid or ion collector, will be collected by this grid. So, I will get a ion current. At the same time, what will happen? You see, when this knockout electron will be collected by this plate. So, there is the increase of current in the electron current. Previously, suppose there is no gas inside, then what will happen? I will get a simple current, suppose a total vacuum, then what will happen? I will get a simple, and the current which is due to this electron which is continuously emitted from this cathode, okay, it is collected by this plate. Now, the gas is ionized means we have electron as well as ion. Ion will be collected by the ion collectors and electron will be again collected by this one. But the change of electron due to the ionized gas, okay, due to the change of electron current due to the ionized gas will be very small compared to the current which is I am getting by II. What does it mean? Suppose previously I am getting some current here due to these electrons are coming down here, I am getting some current I, which is usually in milliampere range. Now, how many ions will be, how many gas molecules will be ionized? Very small, is not it? Suppose very few, suppose if I say that 10 molecules are ionized, then what will happen? What will be change of the electron current for that? Nothing, negligible, is not it? But I will get a ion current. This ion current, even though small, will be measured by some microammeter. So, I can say that this electron, that pressure, okay, low pressure will be, can be measured if I measure this II, because increase of the electron current will be negligible for the ionized gas, is not it? You see the different voltages here, these are 6 volts we have given to the cathode can be directly heated or can be indirectly heated. So, also as in case of the picture tube of our televisions, these are basically indirectly heated cathode, okay. Whereas you will find that we are giving only 20 volt here for the cathode. We have given 400 volt because the electron is to be accelerated through this region, so that it moves very fast with high energy and heat the gas molecules to ionize it. Basic principle is that with high voltage 400 volts, we will ionize some of the gas molecules inside. This is the basic principles of the ionization gauge. Let us look at. In ionization gauge, a stream of electrons are emitted from the cathode. Some of these electrons strike gas molecules and knock out secondary electrons, leaving the molecules as positive ions, as I said. For normal operation of the gauge, the secondary electrons are a negligible part of the total electron current. Total electron current is very, very negligible, because electron current is already existing there, is not it? That due to the electrons which is around the space charge region of the cathode, continuous electrons are moving around. So, whether this gas is ionized or does not or not ionized, it does not matter, always there is some electron that will be collected by the plate, right. That is why I am saying for normal operation the gauge, the secondary electrons are a negligible part. So, the electrons which is generated by the ions, okay, by information of the ions will be very negligible. So, it is a negligible part of the total current. Therefore, electron current IE is same for all vacuum pressures. This is a great advantage, okay. We will see the expressions. The number of positive ions formed is directly proportional to II, ion current, II I am giving the name. Rate of production of the positive ions or ion current II for a given gas is a direct measure of the number of gas molecules per unit volume and thus the gas pressure, right. The positive ions are attracted to a negatively charged electrode which collects them and carries the ion current. Therefore, the pressure of the gas is proportional to the ratio of the ion current and electron current, right, even though electron current is constant. The expression, this is a very famous expression. So, you see this is our relations. This is ion current and this is electron current. This is almost constant, this is a emitter constant S, okay. So, as the pressure if the pressure decreases, I should say the II also will decrease. If the pressure increases at that low pressure region, you cannot give it some 100 psi there, right. These are the pressure increases, this current will increase because more number of molecules. So, there is a more number of ionized gas molecules. So, more, if the more number of ions, the more current, right. If the pressure falls, the less number of molecules, less number of chances of the gas to be ionized, less number of molecules, the lesser chance of molecules to be ionized, right. So, the current II also will be less, right. Where S is called the sensitivity of the gauge, right, and typical value of the S for nitrogen is S equal to 20 torr to the power minus 1, which is 2.67 kilopascal to the power minus 1, right. The exact value of S must be determined by calibration of the particular gauge, right. So, for each gauge is not gas independent, I mean you have like Mcleod gauge and all these things. So, you have to measure it, you have to calibrate it separately for a particular gauge, particular gas and particular gauge also. The value of S is a function of the tube geometry and the type of gas. So, it depends on both the tube geometry as well as of the gas. So, you have to calibrate it separately to find the value of S. The current output usually is linear. So, it is a linear instrument. So, P is directly proportional to ion current, low pressure is directly proportional to ion current. Now, what is there is some disadvantage of this particular gauge, ionization gauge. You see the filament may burn out if exposed to air while hot. Decomposition of some gases by hot filament and contaminations of the measured gas by the gases forced out of the hot filament. So, there is this chance is there, okay. So, because at the hot filament what will happen, it will decompose, it will some decomposition of the gases hot filament and contamination of the measured gas by the gases forced out of the hot filament. So, that will contaminate the gas actually which I am measuring. Okay. In some situation this is not allowed. So, hot cathode ionization gauges covers the range of 10 to the minus 10 to 1 torr. Now, Knudsen gauge is another instrument, even though it is very for scientific applications, but it is do not have an electrical output. You have seen the Pirani gauge, thermocouple gauge, ionization gauge has a direct electrical output, whereas you will find in the case of Knudsen gauge, like your Mcleod gauge, it is basically monitoring instruments. There is no actually the electrical output. Okay, Knudsen gauge you will find it is rather difficult. I mean, you will find that is a, in the case of Mcleod gauge I am getting a manometric reading, whereas in the case of Knudsen gauge a spot of light is moving on a scale which is calibrated in terms of low pressure. Let us look at Knudsen gauge. It is relatively, that is another advantage which is not there in the other gauge like Pirani and the ionization. It is relatively insensitive to gas composition and thus gives promise to the development into standard for pressure too low for Mcleod gauge. Mcleod gauge is not, as I discussed, even though we are using as a pressure standard, dimension pressures can be expressed in the dimension of the gauge, but it is not suitable for the pressure below 1 torr. So, in that type of situation this Knudsen gauge can be used as a pressure standard. You see, these are the diagrams of the Knudsen gauge. We have you see there is a gas chambers here, okay. The gas which we are measuring Pi is inside, going inside. There is two fixed plates, you see this is one fixed plate, you see this is one fixed plate and this is one fixed plate, okay. In between two fixed plates we have a movable plate, this is our movable plate, right, and mirror is installed here, okay. A light spot is moving inside this, falling on the mirror and this is getting deflected and coming to this and it is putting on a scale. This scale is calibrated in terms of. Now, what will happen, it is like this one, there is two plates, heated plate is there, two heated plates like this one, and in between these heated plates there is a movable plate, right, movable plate is inside, right, like this one. Now, see what will happen that now the distance between this heated plate and this should be less than the mean free path of the gas molecule. This is the one condition we have in the case of Knudsen gauge, right. Let us look at the fixed plates are heated to absolute temperature Tf, which temperature must be measured, and the spring restrained movable vane where temperature Tv also must be known. The space between the fixed and the movable plates must be less than the mean free path of the gas whose pressure is being measured. Now, kinetic theory of the gases shows that the gas molecules rebound from the, it is not from, I am sorry, this is from the heated plates with greater momentum than from the cooler movable vane, thus giving a net force on the movable vane which is measured by the deflection of the spring suspension. What is that actually? You see that there is gas molecules inside, is not it, is everywhere. So, these are fixed heated plates with the coil we are heating this and the gas molecules are getting rebounds from this one. So, we are assuming that the gas molecule which is rebounds from this heated plate we have greater momentum than those which are reflected from the movable plates which is colder one. So, what will happen, there is a moment or couple will be act on this movable plate, so it will rotate. So, the light is there, so it will fall on the mirror, mirror will also rotate, the light spot will rotate on this scale. This is the basic principle. Now, kinetic theory of gas molecules rebound from the heated plates with greater momentum than from the coolest movable vane, thus giving a net force on the movable vane which is measured by the deflection of the spring suspension. Analysis shows that the force is directly proportional to the pressure for a given Tf and Tb of the form Pi equal to Kf upon under the square root Tf upon Tv minus 1, right, where F is the force and K is a constant. A range of the Knudsen gauge is 10 to the minus 8 to 10 to the minus 2 torr. Okay, this is a typical range. So, you can see that pressure can be measured, low pressure can be measured by this particular type of instrument, right. Now, let us solve a problem on the diaphragm gauge. In the following diagram, 4 strain gauges are placed over a diaphragm. We have seen this already. 4 strain, we have seen this with Rossets, these type of things are there. So 2 strain gauges to and fro, which will actually sense the axial strain, and 2 strain gauges at the center, which will sense the tangential strain, right. The problem is, for the above arrangement, draw the signal conditioning circuit first of all. Find the sensitivity of the circuit in millivolt per Pascal. Calculate the natural frequency in vacuum. Find the maximum allowable pressure for nonlinearity of 2%. Find the full scale output, right. Data given are that RT, the radius, RT, where is RT, please note. This RT is just the radius where the of a circle on which these the tangential strain gauges are placed, where RR is the radius of the circle on which these 2 strain gauges, which will sense the radial strain, this will sense the tangential strain, this will sense the radial strain, are installed, right. Right, let us go back again, already discussed. So, this is our data given. RT is a 0.015 meter, RR equal to 0.064 meter, diameter of the diaphragm is 15 meter, okay, and thickness of the diaphragm is T, 1.28 millimeter. In the case of Rosset, you will find this quite valid, because Rossets, even though it is large in size, because the diameter will be the circle on which it is placed, the tangentials and the radial will be much less than the diameter of the, is almost, you see it is 0.15, that is 0.075, so it is 0.064, correct. Now, say thickness of the diaphragm T is 1.28 millimeter, Poisson's ratio nu equal to 0.26. Battery voltage Ex or 5 volt, gauge factor is the advanced we are using is 2, and gauge resistance we are saying 120 ohm. Density of the diaphragm material rho is 6 × 10⁻³ kg per meter cube, and the modulus of elasticity for the diaphragm material is 2.1 × 10⁻11 Pascal, right. So, let us look at the solution. This is gauge 1, this is gauge 2, this is gauge 3, this is gauge 4, the output voltage here. Right, Ex. Right, now tangential stress are given by, take a new page, St equal to 3 PR square nu 8T square 1 by nu plus 1 minus 3 1 upon nu small r by capital R whole square, like this one, and radial stress will be given by SR equal to 3 PR square 8T square square. And biaxial stresses, we know that also expressions we know, we will give after some time. Now, let us represent this. We assume the 3p r square nu by 8t square equal to, we are writing capital A. Now, this is a and R equal to 0.075 meter, right. So, I can say ST at R equal to RT is equal to 4.572 A, right. SR R equal to RT equal to 4.344 A. Now, again SR at R equal to R equal to minus 4.285 A and ST at R equal to RR minus 0.139 A. Now, the diaphragm is in the state of biaxial stress, and both the radial and tangential stress contribute to the radial and tangential strain. So, epsilon T we know ST minus nu SR by E. So, epsilon T at R equal to RT, I should say 3.4426 A by E, right. And radial strain epsilon R equal to SR minus nu ST by E. So, epsilon R at R equal to RR minus 4.249 A by E. Let be represented by, suppose this is represented by B, then what will happen, you will know that epsilon T will be given by 3.4426 B and epsilon R equal to minus 4.249 B. Now, the gauge factor is equal to 2, and with the application of the pressure, so I can say that the change of resistance R1 dash will be R3 dash equal to R naught, initial value of the resistance 1 plus lambda epsilon T, and R2 dash R4 dash R naught 1 plus lambda into epsilon R, right. So, the unbalanced voltage will be given by E naught equal to R2 dash by R1 dash plus R2 dash minus R3 dash upon R4 dash plus R3 dash excitation Ex. So, this will lead to substituting all these values of R1 dash, R2 dash, R3 dash, R4 dash. I will get E naught by Ex equal to minus 1 upon 1 minus 0.8064 B 7.6916 B. Okay. Now, substituting all the values, we get that B equal to, if I substitute all the values of B equal to 1.6 into 10 to the power minus 9 into P, unknown pressure, right. So, I will get E naught by Ex equal to E naught by Ex equal to or I should directly write, instead of I not write this, I can directly write that E naught by P equal to minus 7.6916 into 1.6 10 to the power minus 9 Ex upon 1. So, neglecting the term, that means the small value of, it is almost, I should say, almost equal to this. So, sensitivity, I will find sensitivity that is in millivolt per Pascal will be given by E naught by P 7.6916 into 1.6 into 5 into 10 to the power minus 6. So, it will be 0.615 10 to the power minus 4 millivolt per Pascal. Now, for the second part, you see that we know the expressions, that F natural frequency 10.21 pi r square radius of the diaphragm, Et square upon 12 rho 1 minus nu square, this is in Hertz. So, if I put all the values, I will get 1308 Hertz, right. Now, third problems, what we said, that we know that P can be related as 16 ET4, the third part of the problem, 3 r to the power 4 1 minus nu square Yc by T plus 0.488 Yc by T cube. This is our nonlinear term, is not it? So, nonlinearity is introduced due to the second term. So, it is given 488 Yc by T whole cube 2 by 100, right. So, this will give me Yc by T equal to 0.345. So, the maximum allowable pressure from this we can write is that P is, if you can compute this thing, we will get P equal to 371.96 kilopascal, right. Sensitivity S will be given by 615 into 10 to the power minus 4 millivolt per Pascal. So, the maximum allowable pressure is this one, and the full scale output will be given by E naught 615 10 to the power minus 4 into 371.96 into 10 to the power 3 equal to 22.87 millivolt, right. This is the answer. This ends the lesson 19 of industrial instrumentation.